Hello students, in this video today we are going to discuss another topic, that is electric dipole in an external uniform electric field. Okay, so now before we start, let me tell you that if you haven't watched the last lecture, previous lecture, so link is given in the description box, so please watch that video first, okay, for better understanding. So now let's start our topic. So our topic is today's topic is electric dipole in an electric uniform electric field. Okay, so suppose we have an electric field. These are the electric field lines and in this direction. So this is a dipole. Suppose here is positive charge Q positive and here is the negative charge Q negative, and this is angle made by the dipole with electric field is suppose theta, and here is the direction of dipole moment from negative charge to positive charge, negative to positive. Okay, P represents dipole moment which pointed towards positive charge from negative charge, that is the direction of dipole moment, and length of this dipole is suppose twice is the length of this dipole. So now this is the dipole moment, this is the direction. So force on the force on charge Q due to the electric field E will be in this direction, because on positive charge the electric force experienced by the positive charge due to an electric field is in the direction of electric field, remember that, and in the opposite direction the force force on negative charge will be, and this is negative F because it is in opposite direction. So let us take this point BC. Okay, so here this point is A and this point is B, suppose. So AC represents the perpendicular distance between positive and negative charge. Okay, so now suppose we have considered a dipole consisting two charges, positive Q and negative Q, separated by a small distance twice A, separated by a very small distance twice A, be in a uniform electric field E. In an electric field makes an angle theta with the electric field as shown in this figure. So now here you see that force on the Q positive charge. Okay, so force on Q positive charge in this direction and Q negative charge in this direction. So force on Q positive charge will be given by, due to this electric field, will be given by charge into the electric field, right? This gives the force on charge due to an electric field, and force on Q negative charge will be in opposite direction, so this force will be minus Q into E. So the net force on the dipole is F net will be QE plus negative QE, that's gonna give you 0, right? So net force on the dipole is 0, and due to equal and opposite force on the dipole at the two ends, it tends to rotate in a direction in a clockwise direction, okay, so direction of rotation will be clockwise, this way, right? So now what will be the torque acting on the dipole? Therefore let me draw the diagram again. This is the dipole moment, dipole, negative positive charge, theta angle with the field, electric field, and force on Q positive is in this direction along the electric field, right? This is the electric field, and here dipole moment P from negative to positive charge. This is the length of the dipole, and okay, so this is A, B, C. Okay, AC represents perpendicular the distance between the two charges. Okay, So hope you have understood. So now torque acting on this dipole will be given by torque acting on this dipole due to electric field E. That's gonna be force on each surge. We have already calculated force on each surge is given by EQ. Okay, and perpendicular direction. Perpendicular distance between the two charges. That is AC here in this case. So EQ into ASC. Now if you draw the triangle, this triangle ASCB or ABC, whatever you say, and here you see if this angle is theta, then this must be also theta, because this electric field lines I have drawn are parallel here, so corresponding angles are equal. So you know it is simple geometry, and here is ABC, this angle is theta, right? So from triangle ABC we have got sine, AC is perpendicular in this case, and AB is hypotenuse, so perpendicular by hypotenuse, that AC by AB. So length AB is the length of the dipole, that is twice A. So it implies that AC is equal to 2S sine theta. Now let us use this value of AC here. Okay, so then we're gonna have torque tau is equal to QE twice A sine theta. So again we know that Q into twice A, that's gonna be the magnitude of the dipole moment. So here electric field sine theta, E and sine theta. Okay, so here I have written P. P represents magnitude of the electric dipole moment, and since P is Q twice A, that gives the magnitude of electric dipole, right? Magnitude of electric dipole moment, right? So now this is the scalar form of torque acting on a dipole. So we have got the scalar form of torque. This one is the scalar form. Let me write the expression again. So in vector form, it will be this tau. That's going to be P cross E, because these are vector quantities, dipole moment and electric field, and vector product, that means cross product of these two vectors is equal to product of their magnitude and sine theta, right? So this is the vector form. So this is the required expression for torque acting on an electric dipole when it is placed in an external uniform electric field. So hope you have understood this. Now what will be the electric potential energy of this electric dipole when it is placed in an external electric field? Let us discuss that as well. Now electric potential energy of a dipole when it is placed in an external electric field. Okay, so now electric potential energy of a dipole which is placed in an external uniform electric field, that is given by the work done to rotate the dipole. Okay, work done to rotate the dipole. So now this is electric field, suppose this is the dipole, and this is being rotated through an angle, very small angle d theta, and work done is dw. Then work done to rotate it through an angle d theta is given by dw is equal to torque acting on it into the d theta. Okay, so we know the formula of torque tau is equal to Pe sin theta, where P is dipole moment and E is electric field here. So now dw will be equal to Pe sin theta d theta. So we have used this value here. So now you see work done to rotate the dipole from an angle theta 1 to theta 2. This is the electric field, and here is the theta 1 angle with the dipole and between the dipole and the electric field, and it is rotated to another angle theta 2. This is angle theta 2, suppose. So then work done will be obtained by integrating d theta from theta 1 to theta 2. Let me draw the diagram here again. This is dipole theta. Okay, work done is obtained by integrating d theta, which is equal to Pe sin theta. We have already shown that one, from theta 1 to theta 2. P remains constant, so it can be taken outside. So integration from theta 1 to theta 2 sin theta. Integration of sin theta is minus cos theta, so we will get this, right? So we are integrating from theta 1 to theta 2, putting these two, so we will get this result. Now let me consider that theta 1 is taken when the dipole was perpendicular to electric field. Suppose when the dipole was perpendicular to electric field, that is theta is 90 degree, theta 1 is 90 degree, and this angle theta 2, let me take this one as equal to theta. Okay, then we will get theta 1 90, theta cos 90 is 0, then theta 2 is suppose theta, so then work done will be given by minus Pe cos theta, and this work done in rotating the dipole in an electric field will be stored as an electric potential energy of the dipole, right, which is given by the dipole, which is given by U. This U is the energy which is equal to the work done to rotate this dipole moment, that is equal to minus Pe cos theta, and Pe cos theta, P and E are vectors, isn't it? So we can consider that as dot product of two vectors, Pe, right, minus P dot E. So that is the potential energy stored in an electric dipole when it is placed in an electric field. So hope you have understood. If you like my videos, please hit the thumbs up button and subscribe the channel if you are new to my channel, and if you think it is helpful, then share with your friends, and see you in the next video. Take care.